Now we are starting a new section, conservation of energy. So the conservation of energy means that the total energy of a system, the sum of potential and kinetic energy, stays constant. So when we talk about the sum of potential and kinetic energy, we call it mechanical energy. Now take a moment and think about an example from everyday life where energy changes from between potential and kinetic. For example, a ball rolling down a hill or a simple pendulum swinging. And one important note in here is that this principle works only when there are no non-conservative forces like friction acting on the system. So in symbolic form, we can write it as E equals PE plus KE. So E is the total mechanical energy and PE is potential energy, KE means kinetic energy. So the total mechanical energy E is constant, which is equal to PE plus KE. So this means that the summation of initial potential energy and the kinetic energy is equal to the summation of final potential energy and the kinetic energy of the system. So that means initial mechanical energy is equal to final mechanical energy. Now that we understand the concept, let's see some applications of this law in real world situations. Let's look at a simple pendulum, a ball hanging from a string attached to a rigid support as shown in this figure. Now if you pull the ball to one side and release it, what happens to the energy of the system? Take a moment to think about it. So initially when you pull the ball above its resting position, you do work on the ball, which increases its gravitational potential energy. Therefore, at the highest point, the total mechanical energy of the system is entirely its potential energy given by mgh. Now, when you release the ball, then the ball starts accelerating, right? And therefore, it gains kinetic energy. It changes its velocity. Therefore, it gains kinetic energy. And at the bottom of the swing, that means at the initial position of the ball when it was just hanging, what happens to the total mechanical energy of the system? So at this position, the potential energy is 0 because we measure the potential energy with respect to this position. So at this position, the potential energy is 0 since the height is 0. And therefore, kinetic energy reaches its maximum value at this point. Therefore, the total mechanical energy is equal to the kinetic energy at this point. Now the ball does not stop at this point, right? It continues its motion and swinging to the opposite side. Now what is the total mechanical energy of the system? So as it rises, kinetic energy is converted back to potential energy. That means the ball is gaining potential energy again as the height is increasing while losing kinetic energy. And just before it falls back at the highest point, its potential energy is maximum and the kinetic energy is 0. At these points, kinetic energy is 0 just before it falls back or just before it changes the direction. Therefore, the total mechanical energy of the system is just the potential energy at these points. Now this continues again and again. The potential energy converts to kinetic energy at the lowest point and then the kinetic energy is converted back to potential energy at the highest point. And in between, the ball has both potential and kinetic energy. In between, the ball has both potential and kinetic energy. Now if this continue again and again, then why the ball stops swinging after some time? So there is a force that opposes the motion of the ball, which we call as air resistance. So it will decrease the total mechanical energy of the system. So if there is air resistance, then the total mechanical energy is not conserved. And remember, energy conservation is valid only if non-conservative forces like air resistance are negligible. But in our ideal case, ignoring air resistance, the total mechanical energy of the pendulum is conserved, continuously converting between kinetic and potential energy as it swings. Now let's look at an example of energy conservation. Think about a roller coaster or a sled on a hill. Both follow the same principle. So if you pull the sled of your friend to the top of the hill, you are doing a work. You are doing a work. Why? Because you are applying a force to pull and the distance is changing. And this work done increases your potential energy. And at the top of the hill, you will give the sled a push to provide a kinetic energy to the sled. Therefore, at the top, you have a potential energy plus a small initial kinetic energy, right? Next, when the sled and the rider slides down the hill, what would happen? Then this initial energy is converted to kinetic energy. So now the potential energy decreases while the kinetic energy increases. Therefore, at the bottom of the hill, kinetic energy is its maximum. And this is true if we ignore the friction and the air resistance. Then only the total mechanical energy is conserved. So what happens if there is friction? As in practical situations, then it will decrease the total mechanical energy of the system as the work done by friction is negative. And this work done by friction force is equal to the force times distance. And this is negative as the friction force is always in the opposite direction to the direction of motion. Now that we have seen these examples, let's do some problems to apply the concepts of energy conservation. Now pause the video, grab a notebook and get ready to solve them. First, let's try a problem using the law of conservation of energy. So we have a pendulum bob with a mass of 0.5 kilogram and it is released from a position 12 centimeter above the low point in its swing. So h is 12 centimeters. Now the question is, what is the speed of the bob as it passes through the low point in its swings? You are asked to find the speed at this point and h is given as 12 centimeter. Now pause the video and try it on your own first. Let me give you a hint. At the highest point, the bob has only the potential energy, and at the lowest point, all of that potential energy is converted to kinetic energy. Now let's work through it together. Alright, we have been given the mass of the bob, which is 0.5 kilogram and the height is 12 centimeters. So you have to convert centimeters to meters. So h is 0.12 meter. Now at the top, initial energy of the system is just the potential energy. Since it is at rest in the beginning, there is no kinetic energy. So let's calculate the initial energy of the system. So initial energy is just the potential energy and potential energy is mgh, right? Here potential energy means the gravitational potential energy. So mass is 0.5, g is 9.8 and h is 0.12. So you should get the initial energy 0.588 joules. Now at the bottom, potential energy is 0. Therefore, the total mechanical energy of the system is just the kinetic energy because potential energy is 0. Now we can apply energy conservation to the system. That means final mechanical energy is equal to initial mechanical energy. Now the final mechanical energy is just the kinetic energy, final kinetic energy, right? And the initial mechanical energy is just the potential energy, initial potential energy. So this gives us that kinetic energy is equal to potential energy, which is equal to 0.588 joules. Therefore, the equation for kinetic energy is half mv square and it is equal to 0.588 joules. Now we can find v square because we know the mass. Therefore, the v square is 2 times 0.588 joules over 0.50 kilogram. So we can calculate the speed of the bob just by applying the numerical values for the mass. So the speed of the bob at the bottom of the swing is about 1.5 meters per second. Now let's try another example before moving into the next section. Here's another energy conservation problem. A sled and rider with a total mass of 50 kg are at the top of a hill of height 40 meter. As they slide down and travel toward the second hump at 30 meter, suppose 2000 joules of work is done against friction. Now the question is, will the sled make it to the top of the second hump if no kinetic energy is given at the start? So at the beginning there's only potential energy, right? Kinetic energy is 0. So take a moment, pause the video and try it yourself first before I go through it. So what is the answer? The answer is yes. Now let's solve it together. At the top of the first hill, the sled has only potential energy, which is mgh, and mass of the sled and the rider is 50 kg and gravity is 9.8 and the height of the first hump is 40 meters. So you get initial mechanical energy is 19,600 joules. Now as the sled moves, friction does negative work, removing 2000 joules of energy. Therefore, the total energy loss is loss in potential energy plus loss to friction. And the loss in potential energy is mgh, right? And we lost this much of potential energy, mgh. And here h is 10 meter. This h, okay? Therefore, the lost in potential energy is m 50 kilogram, g 9.8 meters per second square, h is 10 meter. Okay, so you get 4900 joules. Now what is the total energy loss? So when the sled moves from this position to this position, this much of potential energy is lost plus the loss due to friction, right? Therefore, total energy loss is potential energy loss plus 2000 joules, the loss due to friction, which is 6900 joules. So the total energy loss is less than the initial mechanical energy of the system. That means the system still has some energy when it is at the second hump. Therefore, the sled will make it to the top of the second hump. So this means the difference between the potential energy at the first point and the second point plus the energy lost due to friction is still less than the potential energy at the start. Therefore, sled will actually have some kinetic energy left over at the top of the second hump. Now so far we have applied the law of conservation energy to different systems like pendulums, hills and sleds. Now let's move into another fascinating topic, springs and simple harmonic motion, where energy keeps switching back and forth between potential and kinetic in a perfectly periodic way. Now let's connect what we have learned to a new idea, simple harmonic motion. So think back to the simple pendulum we discussed earlier. As the ball swings up and down, the potential energy changes to kinetic energy and then the kinetic energy converts back to potential energy. And this back and forth change happens repeatedly. So a system like this, where energy keeps oscillating between potential and kinetic, is what we call simple harmonic motion, or SHM, simple harmonic motion. And the main characteristic of simple harmonic motion is that the energy of the system keeps changing from potential energy to kinetic energy and back again in a repeating cycle. And some examples of simple harmonic motion are a simple pendulum, a spring mass system. Now let's think about the spring system, since we discussed simple pendulum in more detail in previously. So in spring systems, when we pull the mass from its equilibrium position, so this is the equilibrium position. And when we pull the mass from its equilibrium position, that means when we pull the mass from the unstretched position, we are giving a potential energy to the system. And this is the elastic potential energy as we discussed earlier. And when we let go of this mass, it gains kinetic energy and loses its potential energy as it moves back to the equilibrium position. So at this position, its kinetic energy is maximum, just like the pendulum. But it will not stop there. It will pass this equilibrium position and compress a little, gaining potential energy again. And before it reverses back, the kinetic energy would be momentarily zero. Then the mass reverses the direction and this process will occur repeatedly. So in simple harmonic motion, the energy of the system continually changes from potential energy to kinetic energy and back again. Now let's think about what the motion of a mass on a spring looks like if we plot its horizontal position against time. Take a moment. What do you think the graph would look like? Pause the video and imagine the curve. Okay, it's already there, right? So initially we pulled the mass from the equilibrium position. Therefore, at t equals 0, the position of the mass is at x at this point. Okay, and after some time it will move back to the original position where the position is at 0, this point. Next, it will compress the spring moving into the opposite direction from the equilibrium point. Therefore, at this point, position is minus x, right? At this position it is plus x, at this position it is minus x. And again the mass will reverse its direction and passes the equilibrium position and then go back to the stretched position. And this repeats over and over, creating a smooth wave-like graph as in this figure, specifically a sine or a cosine curve. So after a time t, the mass will be at the same position as the initial point. So this time we called as period t of simple harmonic motion. So now let's consider some important definitions from this motion. So as we said, the period t is the time taken for completing one cycle. That means for the mass to return to the same position and direction of motion. Next, we define the frequency of this motion. So frequency is the number of cycles per unit time, and it can be found by taking the reciprocal of the period. And the units of frequency is hertz. And we can define another term in here, which is amplitude, the maximum distance the mass travels from its equilibrium position. This distance, amplitude. Okay. And what is the force that pushes back the mass into equilibrium position again? What is this force? We call it as restoring force. So in every oscillating system, there is a restoring force which pulls back the mass into its original equilibrium position. So in this case, it is the elastic force exerted by the spring, and it is proportional to the distance from the equilibrium point as described in the equation. This is the Hooke's law, remember? Now let's look at one more system. This is the final, okay? A mass hanging from a spring up and down instead of side to side. So think about this. What extra force do we have in the vertical setup compared to the horizontal one? Pause for a moment and think. Now gravity is involved. So here's what happens. When the mass is pulled down and released, then the spring pulls it back upward. So there are two forces then act on the mass. The spring force pulling upward and the gravitational force pulling downward. And at the equilibrium portion, the net force must be 0. So that the spring force should be equal to the gravitational force at this point. And that's the difference between horizontal and vertical spring. The gravity is involved in the vertical spring system. It is not just the elastic potential energy. We have to consider the gravitational potential energy in the vertical spring system. And this system is also an example of simple harmonic motion, where the potential energy and the kinetic energy changes repeatedly. But here, remember, the potential energy of the system is the sum of the two forms, gravitational potential energy and elastic potential energy. So as the mass oscillates up and down, energy shifts between elastic potential energy, gravitational potential energy depending on the height, and kinetic energy when moving. Now, before we wrap up this chapter, let's try a quick exercise together to apply this idea. So we have a mass of 0.5 kilogram attached to a spring with a spring constant K 800 newtons per meter. And the system is on a frictionless horizontal surface. And at the equilibrium point, the speed of the mass is 12 meters per second. So this speed is 12 meters per second. Now here are the questions. What is the kinetic energy of the mass at the equilibrium point? And how far does the mass travel from the equilibrium point before it turns around? This distance. Okay. Now I want you to pause the video and try this first before I walk through it. Alright, let's all step by step. Now these are the parameters given. Mass and the speed at the equilibrium point. Now at the equilibrium point, all of the system's energy is kinetic energy, since the spring is neither stretched or compressed. So at this equilibrium point, x is 0. Therefore, potential energy, here is elastic potential energy, half kx square, right? If x is 0, then elastic potential energy is 0. Therefore, at the equilibrium point, we have only the kinetic energy, which is half mv square, right? And we know the mass, it is given half 0.5 kilogram and speed is 12 meters per second. So all these parameters are given. You just have to substitute and get the answer. So you should get the kinetic energy is 36 joule. So the kinetic energy at the equilibrium is 36 joules. Next, move into part B. Now when the mass turns around at maximum displacement, all of its kinetic energy is stored as elastic potential energy in the spring at these points. Therefore, total mechanical energy is now just the potential energy, which is equal to the kinetic energy, which is 36 joule according to the conservation of energy. The total mechanical energy at this equilibrium point is equal to the mechanical energy at these stretched and compressed points. So these energies are equal. And at the equilibrium point, we have only the kinetic energy, and these points we have only potential energy just before it turns around. Therefore, at this point, mechanical energy is just the potential energy, and which is equal to the kinetic energy, which is 36 joules. Now we know the equation for potential energy. Remember, this is not the gravitational potential energy. This is the elastic potential energies. Therefore, the equation is half kx square and it is equal to 36 joules, right? Therefore, x square is 2 times 36 joules over k. So, we have given k, right, is 800 newtons per meter. So, you should get 0.09 meter square. Now, this is x square, therefore, calculate x, take the square root. So, x is 0.3 meter or 30 centimeter. So, the mass traveled 30 centimeter from the equilibrium point before turn around. So, this problem shows the beautiful energy exchange. At equilibrium, it's all kinetic, and at maximum displacement, it's all potential. But the total stays constant. Okay, great job everyone. With that last example, we have completed chapter 6. So we have explored work, kinetic and potential energies, conservative forces, energy conservation, and finally oscillatory motion with springs and pendulums. Now let's take a step back and look at the chapter summary to connect all the main ideas together. So in the first section, we define work, which is the force times distance, and here we are using only the portion of the force in the direction of motion. And next, power is the rate of doing work. And in the next sections, we discuss about the kinetic energy and potential energy. Kinetic energy is equal to 1/2 the mass of the object times the square of its speed. And if the work done by the net force is used to accelerate the object, then we say that the object gains kinetic energy. Next, the potential energy. If work is done but no kinetic energy is gained, we say that the potential energy has increased. So in here we define two types of potential energies: gravitational potential energy and elastic potential energy. And in the next section, we discuss about an interesting topic, conservation of energy. If no work is done on a system, then the total mechanical energy, which is kinetic plus potential, remains constant. And in the last section, we discuss about simple harmonic motion, one important topic that uses energy conservation. There we discuss two types of harmonic motion, simple pendulum and mass on a spring. And in those two cases, it has those two types of potential energies. In simple pendulum, it has gravitational potential energy, and in spring system, the elastic potential energy is involved. Next, we discuss about the restoring force, which is proportional to the distance of the object from its equilibrium. Remember the Hooke's law. Okay, that's the end of chapter 6. So please go through the practice questions and try to answer the question by yourself to familiar with the concepts we learned here.